Hello everyone, my name is Dr. Rini Paulos. I work in the Department of Chemistry, Rice School of Sciences, and today I'm going to take the topic Mole space spectroscopy. So Mole space spectroscopy actually was discovered by R.L. Mospere in 1955. Now he first made the observation of recoilless nuclear resonant absorption in iridium 191. This spectroscopy is also named as nuclear gamma resonance spectroscopy, and there are various elements which can be used for this spectroscopy like iron, tin, antimony, iridium, etc. This spectroscopy is used to know the nature of bond in solid state chemistry, in knowing the bond length of metal and ligand in oxidation state of metal, and also to know the nature of arrangement of ligand in the complex. The principle of this spectroscopy is based on the recoilless emission and the absorption of gamma rays, and it is important that the atoms of the nuclei of the source which is emitting the gamma ray and the our sample, it should be same. Now Mospere effect, actually the gamma rays are produced from the radioactive cobalt, which when captures electron, it further decreases, its atomic number decreases to 26, it's converted into iron 26 and it emit gamma rays. These gamma rays, once absorbed by the sample, it undergoes transition and it goes to excited state, and we get the spectra. So here what we get, a resonant and recoil free emission and absorption of gamma radiation from the cobalt when it converts to iron, and then we further get the absorption and emission, that which is resonance absorption and resonance fluorescence, which have the same energy in this case. But it is difficult to get this resonant absorption and emission. It is because of the recoil effect. What is recoil effect? We are aware when we fire gun, when the bullet goes out, we experience a backward push. That is what recoil is. In case of this Mospere spectroscopy as well, when the gamma radiations emitted, the nuclei, it experience the backward push, which because of which the energy is lost as a recoil energy, and so the nuclei doesn't have enough energy for the transition. Hence, it is important that our sample should be solid crystal. Here, that is what we shown, that if the recoil energy is increased, the hence the because of the recoil energy increases, the transition could not increase. Hence, when nuclei is present in solid crystal, there is a little loss as recoil energy. The second is Doppler effect. As we are aware that as we have shown in here, the tuning forks both have the same frequency. So or we can take the example, if the vehicle is passing by, we can hear the sound of the vehicle very clearly, but as it is go further away, the voice decreases. So that is the case. If we bring the source towards the sample, the energy increases. So we have given that the shifted frequency, which is shown by the delta mu. So by decreasing the distance between the source and the sample, the energy can be increased, and so the transition can occur. So this is the instrumentation of Mospere spectroscopy. The source is mounted on the vibrator, which is actually, the source is in the room temperature, but our sample always kept in a cryostat, because the sample undergoes in solid state crystal, it always in the vibrational state, so it will have the recoil effect. So to decrease that, we keep it in low temperature in cryostat, and once the gamma radiation is given out by the source, the signals are received by the detector, and the signals are further amplified using the pulse amplifier, and further it is gone to the discriminator, which cancel out all the background radiation, and then the signals are gone to the multi-channel analyzer, which give our data in the form of graph. Further, it goes to the constant frequency clock, which actually synchronize the voltage with the servo amplifier. Then there are three parameters of MOSFET spectroscopy. One is the isomer shift, second is quadrupole splitting, and third is magnetic splitting. Isomer shift is due to the interaction between the protons of the nucleus and the s electrons penetrating the nucleus field. It is actually the density of electrons present around the nucleus. So it gives information about the oxidation state, spin state, and the bonding properties like covalency and electronegativity. Second is quadrupole splitting. It is due to the interaction between the quadrupole moment and inhomogeneous electric field at the nucleus. And this gives the information about the oxidation state, spin state, and site symmetry. Third is magnetic splitting, also known as Zeeman splitting and hyperfine splitting. It is due to the interaction of the nuclear magnetic moment with the magnetic field, and this gives the information about the magnetic properties. Now, what is the isomer shift? Like for say this is for the energy level of the source, and this is the energy level of the absorber. If our energy, if the environment, chemical environment of the source and the absorber is same, the energy level remains unperturbed. But if there is any change in the chemical environment of the absorber, the energy level changes. So here this shift, when we get the spectra, we have seen that there is a shift in the velocity, and this is what the isomer shift is. This happens due to the difference in the nuclear radii of the two states, like our sample and the absorber, and the different electron density. And third is the shielding effect of PDA and F electrons. So this is what I've given, that due to the electron change density, charge density leads to the Coulomb interactions which alter the nuclear levels, and this produces a shift in the resonance energy of the transition, which is known as isomer shift. Second is quadrupole splitting. Now this occurs when there is the electric field gradient around the nucleus. So here the condition has to be that the angular momentum quantum number should be more than half, and it happens when the electric gradient field is inhomogeneous, that is EFG is not equal to 0, and here no magnetic field is applied. So here you can see as I have said, the chemical environment was different, so we have seen this change in the change in the energy levels, and there was a shifting. But when there is a electronic gradient is applied, you can see there is a splitting, further splitting, and this causes the doublet in our graph, and this transition is according to spin selection rule. Third is magnetic splitting. This occurs in the presence of magnetic field, means when the nuclear comes in interact with the magnetic field, and it causes a Zeeman splitting. Now there can be different magnetic field. First is within the nucleus, and one is which is externally applied. So within the nucleus we have B contact, B orbital, and B dipolar, and B applied is the external magnetic field applied. So B contact is due to the S electron density at the nucleus. B orbital is due to the orbital moment of these electrons, and B dipolar is due to the spin of the electrons. So this magnetic field, this causes the split of nuclear levels further into many lines. As you can see, it is according to I will be equal to 2L plus 1, and it removes all the degeneracy. So here as you can see, if we see the 3 by 2 is the energy level, we get the 4 substates. It is again the transition of this within this levels will be according to the spin selection rule, which is equal to 0 over 1 plus minus 1. Now here we have got the 6 lines, so we have got the sextet in the in our graph. So I like to summarize. So the MOSFET spectra, if we have given at the different state or conditions, like when the source and our absorber is remains same, the chemical environment remains same, we get the one peak, and that is unperturbed, it is not shifted. If there is difference in the chemical environment, we get a shift in the velocity and we get one peak, and this is the isomer shift. Further, if the electronic field is applied, the energy level split further, and we got a two lines of transition splitting, and we get a doublet in our graph. And magnetic splitting is when the magnetic field is applied, our substrate further split into substrate, and we get a 6 lines, that is sextet in our this spectra. So thank you.